Next up is the normal force. So let me give you a quick definition of the normal force. It's the force a surface applies to an object that is pushing against it. Usually denoted N. So we usually use a big N. With a big N like that. Okay, when do we want to think about normal force? Right now. So we just talked about the gravitational force and the fact that Hal and Al here feel a force mg, and that's why they fell. That's why they fell at the same acceleration. But right now they're not falling, right? They're just sitting on the table. Are they feeling a gravitational force? Maybe it turns off when you're on a table. No, gravitational force does not turn off. They always feel gravitational force. So the reason they're not falling is there must be another force acting, and it's the normal force. The table is pushing back. They're pushing down, the table pushes back. So to figure this out, so let's see, let's do a quick sketch of the problem. Here's Hal or Al, either one, and typically when we start drawing force vectors on a diagram, for each body, you would just usually draw them at the center of the body. Okay, so because really we're approximating all these things as little point masses anyway. So we'll say mg is down there, and the table pushes back up with a normal force, we'll call it N, and even though it's being pushed right here, I'm just going to draw it up here. I'm going to draw it at the center. It just keeps the diagrams neater, right? So we could say, okay, well, the ball does not fall because the table pushes back with N, normal force. Now, if you really want to analyze it, you want to do a free body diagram. Now, this is a pretty simple case. To do a free body diagram, I could practically just not have drawn the surface, but let's be proper and good and do one anyway. So a free body diagram is where the thing you're trying to analyze, the mass, that's the only thing you draw. And you just think about all the forces on that mass, and you apply Newton's second law. So here's our free body diagram in this case. Here's Hal or Al. They feel mg down, and they feel normal force up. Once you have it drawn, you've included all the forces. You say sum of the forces equals ma. Right? And now we're going to apply this law just in the vertical direction. Okay? It actually can apply to vertical and horizontal, and they're sort of independent. But for now, let's do just one axis, because we're really only considering motion in this dimension right now anyway. So what are all the forces in the vertical direction? It looks like N is 1, and mg is the other. And I'm going to put a vector sign on that. That way we can have g as a vector, it's going to point down, n as a vector, it's pointing up. Since I called them vectors, that puts their metadata in there. Their directions are in there. And those equal ma. Okay. Let's see. But since let's see, so we're trying to figure out what's the situation when the thing is not moving, right? So if we're in an inertial reference frame, when it's not moving, then the acceleration must be 0. Right. So then we want to say this side is equal to 0. And since we're in sort of one dimension, we don't have to worry about the vectors. We'll call this just mg. And we'll just call this the magnitude of the normal force. Okay. So that works. And we'll say, well, g is actually down. If we're just going to call it, if we're going to take away the vector, we have to acknowledge that it's in the downward direction. Right. So now it's negative because it's down. The normal force direction is up. And we just solve for n. What you find in this case is that, sure enough, for it to not move, the normal force has to be equal to mg in its magnitude. Right? So normal forces can get more interesting when you have something on an incline. So you'll do problems where rather than sitting on a flat surface, you might have an inclined surface like this. And then you put something, and let's not make it a ball or to roll away, but if you put like a mass like that on an inclined surface, another property of normal forces to know is they always push normal to the surface. That's why they're called normal forces. They always push perpendicular to the surface. And the other thing about normal forces is they can change between different situations and different bodies. Here, I just told you that these aren't falling because of a normal force from the table, right? But they have different weights, or they have different mgs, right? This one was 18 newtons and this one was 6 newtons. So over here, somehow the table knows enough, it better push back with 18 newtons. And over here, it's smart enough to push back with 6 newtons. So that seems a little weird about normal forces. They're not constant. It's like they know what to do to make something stop. That seems strange. Also, they dynamically respond. Right now, it's 18 newtons to keep it from moving, but now I can push and make it 20 newtons, 30 newtons. Or I can kind of lift it up a little bit and make the normal force be less to make it not move. So it's a little mysterious, these contact forces, how they can respond like that. One way to think about it that I think is helpful is to think of a solid object as a really, really, really stiff spring, okay? The reason that this normal force can respond is you actually are compressing the table a little bit. And when you compress the table, the spring force, which we'll get to on the tour de force, can grow or shrink to whatever you need to make it stop. So the table isn't sentient. It's not applying a normal force that it needs to apply to keep it from moving. It's actually just responding kind of like a spring or like an elastic material. But anyway, you're going to be using normal forces a lot as you work problems, so you want to get used to the idea.